will be fun.
This is our favorite part. Get to see everyone from all over the world. We've got Tel Aviv to Illinois to Seville.
Wow.
So this will be our final special event pre-lecture. The course unbelievably is coming quickly to an end. So thanks everyone for joining. We have James Whitfield here with us today, a member of the Qubit by Qubit advisory board. And he's going to talk to us about his journey in quantum computing. James is an assistant professor of physics and an adjunct professor of chemistry at Dartmouth College. So he will tell you much more about his journey and all of the things he's working on in his research. And then we'll have Kanav, it looks like Kanav is coming on right now. Kanav, a co-founder of a quantum startup. Hey Kanav, QBraid, do a demo of their tool and talk to us a little bit more about QBraid and some of the independent projects you can work on. So I will just stop there. James, if you want to take it away with a more complete introduction of who you are and what your journey is like.
Okay, so let me see if I can share my screen here. I'm very excited to be invited as a guest to the Qubit by Qubit school. So let me see. Okay, you guys can hear me, yes? Great. So I wasn't exactly sure what to prepare for this, so I just kind of gave a sense of what some advice I'd like to impart for up-and-coming scientists, few reflections on my own life. And I'm glad to hear you guys are starting algorithms today, because I'll touch base on one particular quantum algorithm that has a lot to do with this reflection that I'm going to give. So I have funding from a number of different places. As you note here is QBraid. QBraid will give a little demo at the end. My graduate student Kanav, my former graduate student, Dr. Setia, will be giving an introduction. So just to get started, what I wanted to do is just kind of take a reflection on my career path, and think a bit about what has gone through and kind of some of the things to take away from it. And this idea of reflections is very deeply ingrained into what quantum mechanics is about. On the left-hand side here is a technical description of Grover's algorithm, but I think it's not so important. I think the point is, if you want to know what this is about, it says if you take a product of two reflection operators, you get a rotation. It's the core essence of it. You'll come across this a bit later when they discuss Grover's search in much more detail. But for now, we can just think of reflection as a way of swapping things around. So this is one of my favorite paintings by Velázquez. This painting, if you're seeing it on your screen, it does it no justice at all. This painting, the characters in the painting are life-size. So it's a very, very large canvas. It's a very dramatic picture. And it's a picture of the painter painting himself, painting the painting, which is, I think, a really cool way to kind of see a painting. And so it's reflecting, and the king and queen are back here inside the mirror, and they're looking in on their family. And so the royal painters put himself into the painting. And I thought this was an amazing way to think about reflections and what one goes through in order to understand quantum mechanics, understand themselves, understand the things around them, to know whether or not you look nice or not. You have a lot of mirrors around you. And this is what I want to take a second to just reflect on. My career has taken me all over the world. And just to say a little bit about that, well, one quote, I have quotes all over the place. If you wanted the attributions for some of the quotes that just quoted, but there are three methods we may learn wisdom: by imitation, which is the easiest; by experience, which is the bitterest; and by reflection, which is the noblest. So here, I'm hoping you guys can learn from imitating some of my career path, by hearing from some of my experience, and you'll get your own experience by taking this course. This course is not easy, so you have to go through the pain and trouble of learning Brockett notation, linear algebra, and everything else that's going on inside the course. But here today, it's about reflecting. There's already a question. Wow. Will the slides be available somewhere? I can make them available. I think that's not so hard. Okay. So yes, I will say that I've been very thankful. So instead of giving my curriculum vitae, I called it fortuitous vita, which is just saying a very lucky life. There's a famous quote, well, not famous, there's a quote from Nas that says, "Luckily I was put on one of the ships that made it." And on the left-hand side, there's a picture of a slave ship. It's a bit dark, but I think it's also very telling about some of the motivations that I have for doing good work. And I think some of the motivations you might have yourself about thinking what is your motivating factors. For me, I'm very thankful for all the things that I've had, all the things that I've been able to accomplish. Um, just been very lucky inside my life to be able to get as far as I have. I was studying quantum simulation, quantum information way before it became a huge selling point, before there were courses on it, before there were high school introductions. So I've been studying this for over 10 years. I have over 30 articles, over $1 million of research funding. I'm on the board of several scientific advisory boards, frequent panelists, for example, achieving a quantum smart workforce. And I'm also a professor of physics and astronomy at Dartmouth College. Just not to brag or anything of that sort, I wanted to actually say my favorite a game that you can play with yourself when you wake up in the morning is write down a 6-word biography. My 6-word biography that I think fits very well is bottom of the all-star list. I've done very well. There's of course people who've done better, but I think one of the things that keeps me motivated and keeps me pushing forward is knowing that, you know, I was lucky to be here, that I'm lucky to be here. I do my best work every time when I sit down in front of a pencil and paper, in front of a compiler, you know, I'm trying to do my best, right? So if that's not the best in the world, or if it's not the worst in the world, I'm just doing my best. There's no point in thinking that you're not doing well. The point is to do your best and be thankful that you have an opportunity to try. Okay, all right, before I go any further, I would like to share a little bit more about my path. And I have a visual here that I think will help bring everything together. I made this some time ago. This is a map of all the places that I'm from, all the places I've worked at, all the places I've been that are relevant to my career. So I think it's a little more visual than just having a list of places. So I'm from Prince George's County in Maryland. I studied at Morehouse College in Atlanta. This is a school here in Atlanta. I went to grad school at Harvard, so this brown lines representing Harvard. I did 1 year at Pittsburgh and University of Pittsburgh, and I've studied at Berkeley, California a couple times. And I'll mention some of my mentors from Berkeley, California that really got me into research. I'll talk a bit about the importance of mentorship, but at all these places, I've had fantastic mentors, and I've been very thankful to have fantastic mentors. And I think this is also part of the fortuitousness of my life is that I've been able to find good mentors. And I want to tell you a bit about finding good mentors and having good mentors. I also spent 5 years in Europe, bouncing around. I was in Italy, I was in Austria for the longest amount of time. I stayed in Germany at the Max Planck for some time. So just to say that if you do science, there's a lot of opportunity to travel. I guess COVID is a strange event inside of everyone's life cycle, but I guess you can travel virtually now without having to move anywhere. But nonetheless, I've physically moved and lived in these places across the seas. So that's to say that science is not something that you have to be stationary about, and it can give you a lot of places to travel, a lot of places to explore. But in order to be in a position to explore, you have to be ready and capable of doing your part. And so that brings me to the next aspect of my career path that I think is very important for us to touch base and discuss is the importance of mentoring. So motivation and mentoring, when you have a mentor, you have a coach, you have someone who's pushing you, someone who's driving you. You tell your coach you want to be good at something, your coach can tell you to do more. The coach can tell you you need to do this, you need to do that. But a coach will not do the exercise for you. You know, you can't get away with just wanting things. You have to actually go after them. So I think my favorite story that I was conveying just on Friday, I gave a lecture at the University of Southern California. And we were talking afterwards with some of the students about career path and things like that. And we're talking about, you know, someone was reading a book about research. I said, that's very funny. I had a friend who read a book about how to play chess. And they read the entire book from front to back. And then they said, okay, I'm going to play my dad. They played their dad and they got beat very badly because they hadn't played a single game during the entire reading of the book. So you can't just read a book about chess or read a book about pianos and expect to be a piano player or a chess player. In the same way, you can't just learn about quantum mechanics, learn about research. You need to go out and actually try doing it. So to be excellent, you need mentors who care about your well-being. So you want to find people who care about you, people who are good, people who want to see the best out of you. But to get those type of mentors, you need to be working in the first place. You need to be putting forth the effort that's required. The coaches help you get to the next level. They don't get you to get to the first level. You need to be there already. Coaches won't do the exercises for you. And just to give you a sense of who all these people are at the bottom, these are all my mentors ordered from undergraduate to my current mentor at Dartmouth, who's been helping me a lot through a lot of the transitions and things that have happened since becoming a faculty member. This is Troy Story. I think he's retired from Morehouse College. Bill Lester is retired from University of California. I did my first student internship with Bill Lester, where we worked on quantum Monte Carlo and looked at the radical molecules and did this with quantum Monte Carlo. Troy Story taught me quantum mechanics the same way you're learning quantum mechanics in high school. I learned it the senior year of college, so the junior and senior year of college. So Troy Story was one of the most influential people for me actually getting into this career path. So I'm really thankful that he kind of took the time to make sure that I understood quantum mechanics. Finding good teachers is also important. Yes. Then Alana Spiro-Guzik was my PhD mentor. At the time that he was mentoring me, he was at Harvard. He was actually a student of Bill Lester. So you see there's a whole connection of how all these things are connected. Troy Story had introduced me to Bill Lester. Bill Lester's student, Alon, ended up being my PhD advisor. And then I went to Europe to work with Frank Verstraete. Frank is just an amazing person. Frank is, you know, when you talk about people who are geniuses, Frank is actually a genius. It's actually impressive. Frank is also a very fun guy. So if you ever get a chance to meet Frank, you should definitely take up the opportunity, especially if it's involving beer. Frank's a great guy. I mean, you guys are in high school, so please wait till you're of age. But nonetheless, Frank's very nice and also very smart. Some of the work he's done on developing classical methods for simulating quantum systems is amazing. My faculty mentor, my peer, is Lorenza Viola. She's also at Dartmouth with me, and she's had a much longer career than I have. And it's been really exciting to kind of see my career unfold and have her mentorship help me through it. So again, through almost every stage of my career, starting from undergraduate through summer internships, to PhD, to postdoc, to faculty member, I've had excellent mentors who care about my well-being and also care about me doing good work. And so when I feel like I'm not doing what I'm supposed to be doing, or I feel like I'm not doing enough of what I'm supposed to be doing, or I feel like I'm doing too much of what I'm supposed to be doing, you have someone else to kind of temper that and make sure that you take the days off when you need to. Make sure you get the rest that you need to. I think especially now with the situation of everyone being isolated, it's very important to find people who you can connect with, people who you can talk to, people who have your best interests in mind. So let's see, is there a question? What sparked my interest in quantum? So that's an interesting question. My interest in quantum comes out of the fact that in undergraduate, I had a math degree, a math major, in addition to studying chemistry. When I studied chemistry, okay, chemistry is interesting. Nothing bad about chemistry, but when you get past, you know, all these listed reactants and the periodic table and all these things, you start to ask yourself, well, where does mathematics come in? And I remember sitting in Troy Story's class, Professor Story's class, and we started talking about spectroscopy, and you hear the term group theory come up. And this idea of group theory being applicable, when I learned it inside of my sophomore year of college, you know, had no application to physics. It was just a way of looking at symmetries, a way of looking at reordering letters and combinatorics, and really nothing connected to physics. When we get to molecules, we get to atoms, we get to quantum mechanics, the amount of mathematics that has to come in, the amount of mathematics that you need to even have a visual understanding of any of the things we're talking about was amazing to me. And I found that as a really interesting way to get excited about it, because I loved linear algebra. When I went to grad school, I took Alon's class in quantum mechanics, and I'm so thankful that I had taken a upper level class in just linear algebra that had nothing to do with anything to do with physics, but the mathematics that I learned there was really, really interesting to see it applied inside of quantum mechanics. There's more questions. Okay. Valuable double major in CS. Oh man, there's so many things. Okay, particle physics, I'm going to punt on that one. There is a connection between quantum mechanics. So everything below a certain scale, you need to use quantum mechanics for. There's quantum electrodynamics and things. How do I spend time in the lab? Well, right now I'm doing all theory. So you spend your time making sure that the compiler works, making sure that you have your computer set up, make sure that everything's running. So it's actually really nice that we were doing theoretical work before COVID started, because that meant that we could just continue our work almost unhindered. I think the major thing that's happened, as I mentioned, and as we're talking right now, is important mentorship. Mentoring is especially important now when there's a lot of things going on that people are isolated. There's a lot of stresses that come along with that, that I think making sure that people are paying attention to one another is very important. Okay, let me answer the first question here. It says, are there any ways you can come without a grad degree or graduate? So this question about whether you need a graduate degree is extremely interesting, because as I understand, many of you guys are in high school and you're learning about these things that I learned as a senior in college, right? I read books about this. So now you guys are learning about this right now, which is fantastic. So perhaps you know enough that once you finish your undergraduate, you finish an undergraduate degree in quantum information, perhaps you don't need a graduate degree. There were no degrees inside of quantum information science. There were no departments for quantum information science when I was coming there. So that's my answer there. Okay. Interviews, practicing also. All right, so I'm gonna skip these questions for now. I'll come back to them time permitting, but let's just hold on to some of these. We'll answer them. I'll also let Kanav answer some of these towards the end. And just to kind of say who that is. So as I mentioned, the importance of mentoring, you need excellent mentors who care about your well-being. Well, when you get to a certain point, you also get to be a mentor, right? So some of you taking this course, perhaps you love the course enough to come back and be a teaching assistant, to be a tutor for this course. And that's when you can come back and give back the things that people have given you. So as I mentioned in the beginning, a lot of being fortunate is being able to give back. And my first PhD student, Kanav Setia, will talk a bit about some of the things he's been doing since he graduated. But this is my first PhD student. So I'm very proud to see him be so successful. And this is my chance to be a mentor, to push someone to do their best, to make sure that they're doing okay as a human being, also okay as a scientist, okay, and they're reaching their goals. And that's really what mentorship is about. Okay, so I'm gonna move forward a little bit more. So I have a research group at Dartmouth College where we work on a number of different things. So the picture is rather old. You see Kanav still there. A lot of people have left, a lot of people have come, but it's tough to get pictures in COVID era. So we'll get a Zoom picture soon enough. What we look at inside my research group is looking at the computational boundary between quantum and classical. This is a very famous picture from a popular science magazine, Physics Today, by Wolchek Zurich, and he has this very interesting discussion of the boundary between the classical domain and the quantum domain. In the quantum domain, they mentioned particle physics. Well, talking about gravitational waves, talk about electrons, atoms, photons, subatomic particles, all these things are in the quantum domain. You need to talk about quantum mechanics to discuss all these subatomic particles, all these type of particles. However, when we go to something like planets, the sun, people, you can use classical description to talk about it. So this little cartoon illustrating this, and it's an interesting read if you want to. Here's Schrodinger's cat, half dead, half alive, and here's a person standing, classical person. And so our group looks at it not so much as the difference between quantum and classical, but what's the computational difference between quantum and classical? So we're thinking about what is the motivation for building a quantum computer? How do we simulate electrons? How do we understand chemistry on a quantum computer? How can we develop algorithms that use quantum and classical methods? When do we need to use a quantum computer? And these are ideas that we deal with on the regular. Okay, so final words of advice, right? Just then I'll start answering a few more of the questions. When you're young, don't slow down. I really love this quote, especially now that I'm 36, because I heard this quote when I graduated from college, and it's a fantastic quote because you can actually tell how old you are by how much you need to slow down. So if you're young, if you don't have to worry about, where your next meal is coming, get to work. If you are excited about this, get to work. If you are nervous about what's about to happen next, get to work, right? Just do as much as you can. Don't slow down. Just do more and more and more. So that's my major takeaway suggestion. And the more you're doing, the more people will help you do more, right? So you look for your mentors. You talk to your mentors. You just hope for the best. Do your best. Don't worry if you're not the best. Just do your personal best every time you step up. And so let's see. I'll answer a few more questions, and then I will turn it over to Kanav to talk about our quantum computing platform, which is called QBraid. Kanav will give an introduction, but let me answer a few more of these questions before we move on. I'll pick a few, and then we'll leave a few of them to answer afterwards. Okay. particle physics, periodic table, possibility of industry. Uh, All right, so let me answer a few of these monolithically. So a lot of these questions are about the future, right? So the future. So I've been in quantum computing for over a decade. And so to ask what's going to happen a decade from now, I could have never imagined where we'd be now. Right? So when I started my PhD, I thought quantum error correction was a, a cool idea, very interesting physics, very interesting mathematics, but I didn't think it was going to be something people actually built. Now, this is really what companies are pushing for. This is really what things are moving towards. The quote, by the way, is from my still mad at this guy. I don't remember. Professor Ping at Morehouse College, yeah, he gave me this advice right before he gave me a B- for handing in a document 30 seconds late, but I didn't get the honors in mathematics. So I'm still mad about it after all these years. But I like the quote, so that's where the quote comes from the honors mathematics senior thesis, which I wrote on complex analysis. Okay, yeah. So Kanav's going to give a 5-minute introduction to QBraid. So let him give an introduction to QBraid, and then we'll come back and answer more of these questions together. I think some of them will be useful. For example, how to find a mentor in this field. Kanav would probably be able to answer better than me. I found my mentor in this field before it was a field. We just rolled in. We did a lot of things to create the field, and then it was just a bit lucky that the things worked out. You can't always tell what things are going to be 10 years from now. Quantum computing has been going up and down, and so these things are very interesting. So yeah, we'll answer a few more of these questions, and I can even type some of the answers while I hand it over to Kanav to let him give you an introduction to our quantum platform, which allows you to explore quantum computing. You guys are learning a lot about quantum computing. If you want to play around with some quantum programs that go beyond just the QuizKit platform, and you want to test out some other platforms, QBraid's a perfect place to get started. So let me turn it over to Kanav. I'll stop screen sharing, and I'll type a few answers while he's giving the introduction. So Kanav, are you ready? Still on mute.
Yep.
All right, Kanav, take it over.
Cool. So let me share my screen. All right, so this is what QBraid.com looks like. The problem that we're trying to solve at QBraid is perhaps the one that you all may be facing, where if you're going to IBM's platform, you get access to QxQ, but there's no Circ installed. There's no AWS Braket installed. There's no stuff from Rigetti. And then if you go to Google, you can go to Colab, but then you have to install stuff and you have to install QxQ, Circ. Nothing comes and works out of the box. So this is the first problem we wanted to solve. So here you come and you go to my QBraid. The first page you're going to see is this. So this is your landing page. We've built 3 different platforms for everyone. And we wanted to be the place, sort of like an ecosystem. So if you want to study, you click on QBraid Study, QBook. And then on QBook, you have a very nice looking notebooks in HTML format. So it's similar to Jupyter Notebook, but with a lot more functionality. For example, it has a lot more widgets to play with. So if you are, if you like to learn on your own, definitely visit us. We've got videos built and available. And then you can also use it on your iPad. You just click play button, the code runs automatically. Yeah, and you can play with it. You can also change the code. Hello, qubit by qubit, and then you'll see that you can play with it, right? And then you hover over here. This is the whole course outline. So I'm sure you guys are having fun, but this is just another resource if you ever want to explore something more. We'll have more courses available in the form of QBook. We're talking to multiple professors at various universities who will be making advanced courses available as well. Because I saw a couple of questions about, hey, would there be any advanced courses? So yes, in in the following year or within few months, you can expect a couple of courses coming up, which are a little bit more advanced. So our basic version, we're calling it Cubes course, short for Quantum Beginners. The next one will be Quints, short for Quantum Intermediates, right? So once, let's say you've learned enough and you're ready to move on to the next platform, we have Learn available for you. So what does Learn do? Uh, there you are. So on Learn, you click on, let's say, QBraid. So we give you a couple of platform options, and you can, let's say, pick QBraid. Now, if you pick the QBraid, you get the Jupyter Notebook, perhaps you guys are already familiar with, but now Qiskit, Circ, Rigetti's Pikewill, Amazon Bracket, all of those things come pre-installed. So you don't have to install anything at all. You get all of those things pre-installed along with all the tutorials from us, IBM, Google, and Amazon already in your root directory. So when you go to your home directory, you would see a folder, let's see, this one. And you'll see that there's a bunch of stuff that will already be available in your home directory. You'll have tutorials. You can see all the tutorials from Amazon, Google, IBM, from us, a little bit overview of each platform, all good to go. Let's say I go to IBM and I see they have a bunch of tutorials, and these are straight from their GitHub. The Qiskit tutorial, and then you can like pick whatever you want, just open it up, and you'll see that once I open, I just press Shift Enter, and it just works. So you can copy the code, you can play with it, change it, whatever you like. So basically, you never have to leave QBraid to get many of your questions answered, right? And what else? Yeah, moving forward, you can expect a lot more features. We're updating the UI a lot. We'll be adding custom extensions. Hopefully, there will be a feature of chat where you'll be able to chat with your collaborators and so on QBraid itself. Just search the email address or their username, and you'll be able to chat with your friends on QBraid about the project you're working on. And yeah, a couple of really cool features. And then this is again work in the development. You would see that recent papers in the field of quantum computing all available within your um, accounts page. And then all the news articles coming in the industry again showing up here. So this is something that we're still working, and you'll see the upcoming events here. For example, there's this MIT Sloan virtual tech conference that we're presenting at and giving a demo of QBraid. This is here, and there's a bunch of hackathons coming up. There's one hackathon by Stanford and Yale. I recommend, I like encourage you to register for that. It should be a pretty exciting event. All those events would show up here. So basically all your quantum world, we want to bring it into a single place, your knowledge, and then the ability to do a lot of it. Then once you become researcher, we have research.qbraid.com available. Here, the concept is we provide you a sandboxed environment for each of the quantum package so that they don't mess with each other. So if you're developing production level code, you'll make sure that your environment is sandboxed and it doesn't break. And it just opens up another Jupyter Notebook environment where you can get started. And like it feels a lot similar to Learn, but it's more sandbox and more reliable. Yeah, so that was a little bit overview of QBraid. Let me know if you guys have any questions.
If I can say one thing to just tag on here, Kanav, can you say how much it cost?
Oh, it costs $500 per month. I'm kidding. There's no cost.
You should
So
say it's free.
it's free. I was kidding. So the basic tiers, we envision it to be free. So please go ahead, try it out, register for it, play with it. we're happy to get your feedback and excited to. You've got recommendations for new features, please let us know. We work super hard to get as many features as possible for you so that you could do the best of your work. Yeah.
Okay. So Kanav, we have, I think another 10 or so minutes, maybe 15 minutes even. We should just tag as many questions as we can. I'm looking at a lot of them. They're asking is QBraid commercial? It's free. It is a commercial entity. We are actually a company, but it is not designed. The educational aspect's not there for making profit at all. We also have a question here that says, is D-Wave included?
Yeah, D-Wave is included.
Which is interesting. D-Wave does not have a full-fledged quantum computer, so they have a quantum optimizer. Are we hiring interns? There is, I believe, a call for interns as well, right? Do you have the link?
Yeah, just go to qbrave.com/careers and you'll see a lot of job openings for intern.
The motivation for the QBraid name is interesting because when you have these quantum particles that people use, instead of having fermions or bosons, which are types of particles, you have these anyons, which you need to braid in order to do computation. And so we're thinking about quantum braiding. So that's where it's from. Penny Lane is on there, right?
Yeah, Penny Lane's on there. Again, like if you
We don't have Julia though, right?
We don't have Julia, but that's a good
Okay.
recommendation. We'll work to make it available. It's just like right now, quantum computing is mostly happening in Python. So that's where we've been focusing our energy. But if you don't see any package available right now, do let us know and we'll be happy to make it available. Yeah, for example, D-Wave, we ran MIT's quantum computing hackathon this past January on QBraid. And so they wanted D-Wave. So we worked with them, made like D-Wave available on our platform. So that is available right now. And so Qiskit is the SDK, QBraid is company integrating all of utilities like software.
This is very exciting. I'm glad you guys are asking so many questions.
Yep.
Yeah, there's a lot of things for internships, just as a general comment on internships. Right now, the quantum industry is really booming. So there's a lot of opportunity to get internships, both for QBraid and all over the place. So when you start looking for places, you need to, like, as I said, be working already. There's a lot of people who are also looking for internships as well as a lot of internships. So if you are already learning, you're already taking part of this qubit by qubit coding school. So you're making the first step already. I think that'll go a long way for helping you get an internship down the line. So I think you guys are already taking the first step. I think that's an important way to get started.
Yeah, and then I see a question about answer live. Okay, what happens if I click on answer live?
No, you just answer it live. They're dropping them off for us.
Ah, cool. So yeah, so one important point, yes, you can run a lot of calculations on IBM's actual computer from QBraid. So you just need to get that SSH token that they give you, put it in wherever they tell you, and you should be good to go. You should be able to run a lot of the calculations on IBM's machine, on D-Wave's machine from within QBraid. In fact, I think there was this program by the coding school itself last year where a lot of the high schoolers ran their their calculations on IBM's actual hardware from QBraid itself. And then, yeah, people also ran calculations on D-Wave through QBraid. Can you tell?
Yeah, can you say a little about your educational journey? That's actually really interesting. You have an interesting one. Kanaf started off as an aerospace engineer.
Yeah. So yeah, I basically started. I would say start a little bit early, like my school days. I was really dumb kid. My parents didn't like imagine me finishing up even college. Forget about PhD. But then I ended up like falling in love, absolutely in love with physics. But then for some reason I went and did engineering, after which so it was first aerospace engineering in my college, and then I switched fields to semiconductor industry. So I worked in fabrication facility, which is very similar to doing a lot of experimental physics. That's how I convinced Dartmouth to let me in so I could do experimental physics. I got here, worked on experimental physics for 1 year. Then James showed up. I was like, okay, I'm switching.
Good decision.
So I ended up doing theoretical physics and a lot of quantum simulation. Thanks to James, he was like amazing. When you're starting off switching fields, it's just so much learning, and it requires a lot of patience from your mentor. Which I'm so happy to tell you all that James had that patience with me, and he put in like a lot of time. And yeah, I ended up doing good work, getting a PhD, starting a startup in quantum computing. Okay, this is done.
Quantum
And
machine learning. Oh, this is a really interesting one. So quantum machine learning is two ways that you have quantum machine learning, where you're using quantum mechanics to do better machine learning, and you also have machine learning to do better quantum information. So you get quantum machine learning coming from two different directions. That's quite interesting. It's a rapidly growing field. Machine learning is also extremely exciting field that's developing. It's developing alongside the quantum, so there's a lot of crosstalk between the two. So hopefully that answers your question there. Requirements to be able to do open source projects in quantum computing. Kanab, are we still making this? We're making a repository of projects, right, for QBraid. There'll be a lot of small projects that are designed that are just like coding up the Grover search algorithm. That is just a real in the box sort of a project. It's not necessarily a research project, but a very nice project to do to learn something while you're going through it.
I would say start small. Look, if you guys are starting, so this is your preliminary, the first course you're taking in quantum computing, right? So I would imagine it to be a little hard to work on the research problems right now, but rather you should pick like small instances. Try yourself coding up Grover's algorithm, try yourself coding up phase estimation algorithm, try yourself coding up Shor's, or go through various QxQ tutorials, understand the code, a lot of the code that is available there already. And once you're doing that, hopefully you'll have a lot more fun. And I would imagine it that you would take like 1 or 2 years before you get into a position where you could handle like some research problem. Let's see, is there a possibility to do?
Yeah. So does it rely heavily on simulation? Are specific simulation platforms used commonly for research? Python has been an extremely flexible language in that there's a lot of other languages that people write simulation code in, C++, Fortran, a lot of different algorithms people write them in, but Python often gives wrappers to it. So you can get a GitHub package that might have an entire half of the package written in Fortran, half the package written in C++, and you can run that simulation package from Python. Similarly, when you're trying to simulate quantum mechanics, you can simulate it with Python packages, or you can actually log into a place like QBraid or to whatever platform you're going to use, and then actually send jobs to the device. You can simulate the device before you send the jobs and actually see whether the device is working. I find that a lot of the quantum experiments that people are doing now are simulations as much as experiments, as much as computations, right? The computer's not working so precisely that you really have to test it out to see if it worked. It says a little bit about your work/writings. So we write a lot of scientific articles trying to push forward the field. For instance, Kanav worked on fermion to spin transforms, which allows us to do simulations of fermions on quantum computers. This is one of the major areas of research inside my research group. We've had a number of undergraduate students get started in our quantum group, and Kanav even mentored a few of them. So what we normally have for undergraduates now is that they come in, do a reading project, and then they do a technical project where they try and contribute to something that involves their ongoing research, perhaps testing out some code, extending something, seeing what happens. So hopefully that answers that question.
And does this platform have an app for updates, etc.? Oh, yeah. So we're constantly updating stuff on our end. And the idea is for each update that comes from, let's say, Qiskit, Circ, we make a new environment. So you don't have to worry about it. So if you're writing your code, that would always work even when there are updates. So nothing would break.
So Kanav, here's a good question. It says, what made you start a startup?
Oh,
Kanav started the startup. I'm following Kanav into this. I've gotten dragged into the world of business by Kanav.
Well, so that's a good question. I don't know. So it seemed like there was a need for another company where we could actually contribute, build something, and then startups are always fun. Like if it works out, you just make so much money. I mean, like so that was one of the biggest reasons where it seemed like, hey, it'll probably be the same stuff that I'm doing anyway. A lot of writing code, a lot of physics, and I'll still be doing quantum computing, but instead of getting paid a fixed salary, there's a upshot of like much bigger stuff. And if that happens, then
Maybe.
basically, you get to do a lot more cool stuff later in life, right?
So there's a question about the Grover search slide. I've given this talk where it's a little more half technical, half personal. In Grover search, you basically do a product of two reflections, and that's the mathematics I put there without going into any depth. There's actually a set of lectures that I gave in Italy about Grover search and all the extensions of it that are all around this idea of reflections on Hilbert space. So I could say a lot more about it. Let me say, I teach courses in this. So I think at the level that you guys are at, you're going to get into quantum algorithms today. But as you're going through and learning about quantum algorithms, I would urge you to think about all the quantum algorithms that gives you quadratic speedups. All the ones that give you quadratic speedups are really around this product reflections idea. And you'll see this over and over again inside the quantum literature. So I think it's very high level picture about that time and for the sake of pedagogy as well.
Right. Then I see next one. Can you tell us more about the chemistry of on QBreak? Oh, sure. So quantum chemistry, area of my expertise with James. So the idea was IBM was developing their own version, Qiskit chemistry. Google has its own version, Open Fermion, and the pipeline of doing a quantum simulation, understand and writing code that works well on a quantum computer, it's just so long. First, you need to run an approximate calculation on normal computer. You use the result of that, transform that to a new to qubits, and then set up another algorithm. So just understanding the whole pipeline is pretty long. So that's where we wanted to make that pipeline super fast. So we ended up developing a graphical user interface. The idea is you set up the options that you want to run, and we generate the code for you. Right. So you say, I want to run this molecule. We write, like, generate all the code that would enable you to run that calculation, that then you could just press enter and run the code, get your answer. Or you can also understand what the code is doing and modify it to do something different. It's not available yet. It should be in like coming months.
Yeah, so I'm answering one question. It says a graduate student about to join a PhD program in condensed matter, computational condensed matter. I think if you're doing a PhD program in computational condensed matter, it's a very smart thing to do. And I give one suggestion for everyone who's thinking about doing a PhD. I wouldn't worry too much about the job aspect of it. I wouldn't go to a PhD to get a job. I don't think that's the right reason to do a PhD. It's just too much, right? You do a master's degree or just do an undergraduate degree. Go to do a PhD because you love what you're doing. You want to take some time to focus on it. You have 5 years. No one's asking about funding. You get a mentor who's there to help you focus on what you're doing. Do it, do your best, learn as much as you can about your subject. And then when you're done, you now know a lot more and you can say you're a doctor 5 years later, and most of your friends are probably switching careers anyways. So you just take your time, do your PhD in whatever topic you find the most interesting with the mentor you find who's going to give you the best support. And then you finish your PhD, then you can see if quantum computing still, as hot as it is right now. Right? So if you finish your PhD now, I would definitely turn a little bit towards quantum computing as a postdoc. But if you're doing a PhD, do it out of love, is my suggestion.
Yeah, PhD is a bad way to make money.
It's not the point.
Yeah.
Am I still open for mentoring? Yeah, mentoring PhD students right now, mentoring undergraduates and everybody. So yeah, we just finished doing admissions for Dartmouth, but if you want to apply to Dartmouth, please submit your applications in the fall. If you're a high school student here, feel free to apply to Dartmouth. We are excited to look at your application for 2022. Same thing for PhD programs as well. We just finished admitting the PhD candidates for this year. So it's a lot of exciting times, and just, keep up the good work. Going through something like Qubit by Qubit will do a lot to make your PhD look, make your application look even stronger. It says,
Yeah.
Nav, how do you suggest getting the quantum roles as undergraduate from developing countries like India?
Oh yeah, I would say just take like courses like this one, build your CV, and then apply for graduate schools. Or like if you're still in high school, apply for undergrads. And once you get admitted, it's much easier. I think there are a couple of really good places in India as well. Try for IITs. IISc has like some really good programs. Yeah, otherwise, I think at this point, pandemic has made this thing clear where good work can be done remotely and resources are available for everyone who wants to learn. Just the way we're so happy to help out anyone who is interested in learning. We're here happy answering your questions, making our resources available to everyone so that everyone could learn. So let's say if you learn good amount of stuff from this course, end up doing a good project, almost anyone will be happy to take you, right?
Yeah, like I said, get to work. When you start doing good work, it'll attract the people who will help you do better work, right?
Yep.
It says here, it says that I'm heading the quantum information science at Dartmouth. Please, that's not true. I am a member of the quantum information science at Dartmouth. I'm very happy to be a member of it, but there's senior colleagues. I'm also not tenured, so a lot of reasons that I wouldn't want to call myself the head of it. But the program there is that we just have a lot of interest in quantum information science at Dartmouth. We have a number of faculty who are all working in quantum information science, both experimentally and theoretically. As I mentioned, Lorenza Viola also works in quantum control. She's thinking about how do we actually control a single qubit, how do we actually build devices and actually control the devices with pulse level engineering. How do we mitigate errors with taking into account control errors? And so that's her work. My work, and consequently Kanav's work, is more about quantum algorithms, thinking how these things fit together. And we have a number of experimentalists as well. Looks like we're getting cut off. Rachel.
Not cut off at all. This was incredible. I want to pick up on Rishi's question. What aspect of quantum computing, computer science, physics, engineering, and math do you enjoy the most, and which do you enjoy the least? But I want to kind of put a spin on that and just hear, like, what inspires you about this field? What do you want students to continue to find excitement and curiosity in? Where do you find your inspiration?
So I'll take it first, and then I'll let Kanav go afterwards. But I'll say for me, my favorite part of doing quantum information science is that you can do all of those things. You can do all of them. That you can hop from doing a paper on computer science one day to doing a paper on algorithms the next day to reading about physics and thinking about how this applies to quantum phases of matter, and you just hop in from one to the next. And I really like thinking about a lot of ideas at once at the same time. And so for me, it's been fantastic to be able to just go in 15 directions at once and still be doing something useful, right? A lot of times you move in too many directions, you're not going anywhere. But in this case, you can actually explore a lot of things and do a lot of things. I'd say my least favorite part is that there are 50 different directions to move in, and there's only 24 hours in a day. So I'll say that's by far my least favorite part of being a human, is that you have to be limited by time and space. So, Kana.
Yeah. So my favorite part is if you've learned when you started, perhaps you would have learned the first thing called superposition. And so when the first paper on quantum computing was written by David Deutsche, he proposed it as a way to show that because quantum computers work, it means we're living in a world where we have parallel universes. So in quantum mechanics, you have a state where a particle could be in two different positions, and you have this wave distribution. And then when you measure it, it collapses in one location. And so one of the explanations is called the many worlds theory. It says when you measure it, if you're getting this output, then you are in this branch of universe. And there must be another universe where the other possibility happened. So every time you're measuring qubits, you're actually making the universe go into two separate ways and creating two separate universes. It's mostly fantasy, but at the same time, it'll be really cool if that was the case, you know. So that's like scientific motivation comes. Yeah, I love that.
Yeah, me and Kanav had many arguments, discussions about this inside of my office back in the day. So there's a lot of philosophy involved inside of quantum mechanics that I think is really interesting to touch base on.
At the end of the day, like the curiosity is in you is what makes you a scientist. So that's basically, yeah.
Specific food that graduate students eat? Kanav? Is there specific food that you eat? I don't know if that's really.
Yeah, peanut butter sandwich,
They said ramen.
all you can afford on graduate.
Rachel, were there any other questions that we should answer before we close out?
I think that was perfect. Maybe just one final word if you want to close us out, and then we'll shut down this webinar, give people a few minutes before we have a lecture with Fran. So parting words.
Yeah, so my parting words, I think this is a relatively young audience. So again, I'm just going to reiterate some of the quotes that I had earlier. Just do your best work at all times. And while you're young, don't slow down. Don't be intimidated. You know, if you're, I think actually Kanav gave me a quote once and I really enjoyed it. He said, you know, maybe I shouldn't attribute it to you, but he said sometimes if you feel like you're inadequate, you're not doing enough, or you're not doing the right thing, or you feel dumb, you know, don't let that stop you because it's not helping you. Like, so what if you are, right? This is not going to make you any smarter to think that. So just do your best, right? There's no point in like dwelling on it and just, you know, berating yourself over it. So I think with these issues of confidence and elitism and things like that, and bias and gender bias and you know, racial bias and all these things that are coming up to light, my suggestion is just do your best at all times. I think Kanav said that this course, the professor was not giving him the grade that he thought he should get. I said, did you get every answer right? And he said, no. And I said, well, get every answer right, and they can't mark you off, right? And that's my advice: is do your absolute best, and don't slow down. Kanav?
Yeah, I mean, like, think about this thing. If the field grows, we may have the right tools to explore whether the parallel universes exist or not. So that's like a motivation for lifetime. You all need to work so that as a field, we could do a lot more cool things. A lot more smart people need to contribute interesting ideas, and that's how progress happens.
Perfect. I think I froze for a minute, but it seems like we have a perfect note to end on. Thank you so much, James and Kanav. We really appreciate you spending part of your Sunday with us. And with that, we will we'll shut down this webinar for students just for the next 5 minutes or so Fran can get set up, and then we'll be back at 2 Eastern, so 6 minutes to learn about quantum algorithms.
Thank you guys so much for the invitation. I'm really excited to be here, and hope you guys enjoy the rest of the course. Bye-bye.
Bye.
Thanks so much.